Start in another minute or so, give some people some more time to join in. I think we can start now. Yeah. All right. So my name is Asim Rajapade. I'm an incoming senior in Monte Vista High School, and today I'll be holding a workshop teaching all of you about the field of paleontology and the fossils that you'll be learning about today. So I don't know what this is, but so just a few rules and disclaimers before we start. During this workshop, please be courteous to the instructor and don't disrupt the rest of the class. Don't abuse the chat functions because me as well as the other STEM CA can see what you're doing and learn something and have fun. And just a little disclaimer that if you guys are being disruptive, we do reserve the right to remove you from the workshop, unfortunately. And this information is made by STEM Boost and should not be reproduced without our permission. And any of the images used here, any of the images, links, videos, any pieces of media do belong to the respective copyright owners. So let's first start off with the basic need to know. What is paleontology exactly? So paleontology, the cookie cutter definition, is the study of ancient life. This can range from anywhere between a couple thousand years ago to 100 millions of years ago, and can cover a wide range of species from dinosaurs, plants, fish, insects, mammals, fungi, microbes, bacteria, even the first signs of life of cyanobacteria and stromatolites. And the purpose of paleontology is to reveal how organisms change over time, how evolution has progressed in relation to its history, and what our planet was like long ago and the conditions that enabled life to first appear and develop. Paleontology matters extremely much in looking and predicting a future evolution of organisms. And by piecing together what happened to the organisms in the past and how they lived and how they went extinct, we can predict future extinction events and what drives animals to go extinct in the first place, as well as what drives animals to further evolve and how the process of natural selection works. And this also can help us genetically modify animals and eventually humans to force evolution and to better suit us for potential changes in the Earth's environment, especially with global warming now, some unintended activity, or maybe even another meteorite strike. No one knows. Paleontology may seem very straightforward, and you wouldn't be wrong at all to assume that. It is very straightforward. A bunch of scientists go out to the field, they find a good dig site, they uncover some bones while digging, ship them off to a museum. Let me admit this guy that joined in. Paleontology, yeah, it's pretty straightforward. You just go to a dig site, you find some bones. It's way harder than it sounds. But once they're shipped off to a museum or to a lab, they research on them, and paleobiologists who aren't the ones that go into the field, they're the ones who actually work on the bones and the recovered matter, not only bones, but also coprolites, maybe some skin, eggs, and they try to piece together how these animals lived and try to recreate their life. But the technology that these paleobiologists use and the conditions that the paleontologists work with, and discovering the surrounding habitat and recreating the lifestyles and behaviors of these animals using simply bones and the position of the bones in the geologic history of the area can tell us a lot about how these organisms lived and how they sort of evolved and what connections they share with their modern counterparts today, such as the theropods' relationship with modern day birds. Some of you may know the velociraptor, or not the velociraptors, but specifically, but the dromaeosaurid family were the primary evolutionaries who eventually evolved into modern day birds. And so by studying these old bones, we can see how some of the behaviors from these dinosaurs carried over to birds and potentially even artificially recreate some of these smaller dinosaur builds that we saw back in the Cretaceous period at the end of the Mesozoic era. Our perception on not just dinosaurs, but ancient life as a whole has changed relatively in an insane amount over the last decade. Uh, just specifically this last decade, our understanding of these dinosaurs and of course other ancient life has has developed drastically, and especially of course like the last couple centuries has been incredible. But this last decade specifically has been the most impactful. And these quote unquote relatively stupid and overgrown lizards that we used to think of them and were introduced to when first learning about them, maybe when we were like 5 or 6 years old watching Jurassic Park or something, weren't even close to their true image, their true colors. They weren't only limited to some more of the developed viewpoints, such as feathered or smaller or being relatively social. These dinosaurs were very diverse in lifestyle and behavior. They could hunt either alone in packs, maybe mating pairs, social units. They could even form alliances with other dinosaurs and live in symbiotic relationships. They can evolve into birds. The evolution speciation of these dinosaurs can offer clues as to how evolution works in the first place and how natural selection has changed over time while favoring animals better suited to Earth's environment back millions of years ago. And each new fossil that we find helps us fill in this picture of dinosaur evolution and the history of natural selection and how we can use this to predict the future outcomes of natural selection and the future evolutions of animals. Feel free to go into the chat for any questions that you may have. Some of this might be extremely new material to you guys. So if you don't understand the concept, or if you're struggling to understand what I'm saying, or even if I'm just going too fast, let me know in the chat and I'll respond. So here we'll be looking at a case study with the Tyrannosaurus rex. I'm sure all of you know what the Tyrannosaurus rex was, even vaguely. It is one of the most, if not the most famous dinosaur in popular culture, and basically everyone knows about its crushing bite, its size, and of course its puny arms compared to its body size. And as popular culture normally depicts anything, any sort of myth, any history, it does tend to skew the facts and fabricate some of them to better fit whatever medium they're put in. And this has affected the T-Rex specifically, of course, with the extreme success of movies such as Jurassic Park. This led to many people believing that T-Rex was stupid, slow, couldn't see moving targets, and these myths prevailed for many years. But technology used by paleobiologists have broken down quite a lot of these myths with an overwhelming amount of evidence. And they did this through CAT scans and digital remodeling. So what I'm going to show you here. And this is the results that the CAT scans showed us. So here you have the T-Rex's brain. It looks small compared to its body size, but this is pretty big for a dinosaur. This actually rivals the chimpanzee's brain-to-body ratio, or not brain-to-body ratio, but just brain size. And the main thing that you want to look at is the olfactory bulb. So this whole, most of this green stuff, not this big one here, but this one, the bulb at the end of the tract that's labeled here, the olfactory organs in the brain are massive, and this gives the Tyrannosaurus rex a great sense of smell. So already it cancels out the myth that T-Rexes can't see moving targets because they have incredible sense of smell. So no matter if you're moving still or if you're moving or standing still, it's going to see you. And this sense of smell is one that's typically actually seen in scavengers nowadays. So animals such as vultures commonly have large olfactory bulbs to smell out carcasses that may be rotting in maybe a couple 20, 30 miles out. They can smell it. And there have been a few paleontologists who have put forth the theory that the Tyrannosaurus rex was a scavenger, used its size and bone-crushing bite to scare off other predators that may have gotten kills. But these most likely are, T-Rex obviously did scavenge some. Every predator does. Who doesn't scavenge? But the theory that the Tyrannosaurus rex was just a pure scavenger remains unproved, and it was most likely as well a predator. But the rest of the brain is also pretty impressive. It has a large cerebral hemisphere, and its eyesight is pretty good for a predator of this size. Most predators at this time employed mainly senses of smell, but the Tyrannosaurus Rex had pretty good eyesight for a predator of this size. Um, and yeah, I'm pretty sure that's it for this CT scan. And yeah, so I've talked a lot about dinosaurs here. I've obviously tried to mention other ancient life, and we will go on to more ancient life here. Because paleontology, of course, isn't just about dinosaurs. It's about other animal and plant fossils, even though uh, paleontology, most people relate paleontology with just dinosaurs, and most people are hooked into paleontology because of dinosaurs. A lot of other plant and animal fossils give us just as much information into into these into the Earth history and the history of evolution as dinosaurs did. There were many different types of species back then. There were large armored fish, sailback reptiles that patrolled the land for 30 million years, and of course more famous organisms such as the saber-toothed cat and the woolly mammoth. And these organisms dominated the Earth for the time that they lived in. Maybe it may be like 20,000, 30,000 years to a couple hundred million years, and they're spread across the time of Earth's history. It tells us how evolution and natural selection changed over the history of Earth and what led to these builds dominating the ecosystem of Earth for millions of years, and what caused their speciation to not be favored. What changes in Earth's history caused their speciation to die out and caused or forced them to evolve. Here we have a geologic timescale. So this monitors the span of time from Earth's start here in the Archean, where the Earth first formed, to the Proterozoic, where life just starts. You can see little prokaryotes. And then you have all these different periods. We have different eras, the Paleozoic, the Mesozoic, and the Cenozoic. And we have different time periods here. These spanning here you'll see later in other case studies aren't exactly time periods, but this is how most people divide this Cenozoic era. You can see also how life evolved. You have more invertebrates, then you start getting the first basic vertebrates, and then you have mass extinction events, of course, marked here. This is a pretty basic cookie cutter diagram just to introduce you to the concept of a geologic timescale. And then you get, as you get up close, you get the reptiles dying out, more mammals starting to show up in the time period. And then you have humans, of course, at the top, because we're still learning. So we'll take the first look at the how Earth's ecosystem evolves over time and the species that were favored by natural selection. So starting with the Paleozoic. So if we go back here, you can see that the Paleozoic is where life really first starts. And that happens in the Cambrian explosion, where the first vertebrates start appearing. Invertebrates of obviously they did live in the Precambrian era, but they weren't as common at all. They didn't have the near size, the armor, the defenses. They weren't that big. They didn't span the Earth nearly as much. I don't believe even 25% of the Earth's ocean, because there was no land-dwelling organisms at that time. Even I don't think even 25% of the Earth's oceans were inhabited. But here in the Cambrian explosion, this all changes. The first animals with skeletons or exoskeletons start appearing, such as the trilobite, and if you go back here, the Anomalocars. I actually don't think it's on here. But also at the end of the Cambrian, towards the end, we got the first vertebrates. These are small, tiny fish. They have backbones, they have tails, but they are tiny. They're no bigger than maybe your palm. And they don't have fins yet. They're like eels. They're like tiny little eels. And as we move into the Ordovician, it's not marked here, but this is where invertebrates start really becoming massive. You have giant squids starting to appear. You have very big scorpions. You have trilobites expanding even more. And also the first land plants start appearing in the Ordovician. So this is where life on land first starts, if be it only from the kingdom Plantae, not Animalia. But then you move on to the Silurian. This is where life starts to take place on land, but it starts with arthropods with the sea scorpions. And the sea scorpions are the first ones to really get onto land, but also the first jaw bones appear. The first actual teeth, mouths. These jawed fishes also are the first ones to exhibit routine behavior, such as normal salmon migration patterns. Today, where they go back to their spawning areas to lay their eggs, these fish, instead of laying their eggs wherever, they go back to a certain spawning area to lay eggs. So this is where we first see this hoarding behavior. And yeah, vertebrates are still at towards the relative bottom of the food chain. The arthropods and the invertebrates really do have a hold on the ecosystem and the biosphere of Earth. But this all changes during the Devonian, where the first insects start appearing, which is pretty small. Seeded plants also appear, which is also kind of small. But the big thing here is the first land vertebrates. These are the first amphibians. They still have to rely on the water to lay eggs, get moisture, but amphibians are the first organisms to really take control of the land. Previously, in the similarity of the sea scorpions, were the ones to go onto the land, but they didn't really live there. They lived in the water, but they only crossed the land to actually do what grizzly bears do nowadays with salmon, and to catch the salmon as they jump the waterfall. So like that, they try to catch the fish as they cross into the spawning area. And but the amphibians are the first ones to really take control of land. And also during the Devonian, the ocean becomes a lot more dangerous. There is the first armored fish, the very famous Dunkleosteus, starts appearing. This is a armored fish the size of a school bus with a I forgot the actual bite force, but I'm pretty sure the bite force rivaled that of a Tyrannosaurus Rex. Although it had no real teeth, it didn't really eat it. It just crunched down and destroyed any prey. And armored fish start appearing, more armored fish, and also the age of sharks is also the Devonian. So sharks are the ones that, besides the Dunkleosteus, take over the oceans as well. And here we have these two periods, the Pennsylvanian and the Mississippian. Together, this is called the Carboniferous. I don't really like the split of two periods, but it is what it is. Most people just still refer to this as the Carboniferous. It's just that there is two sub-periods here too. The Carboniferous is where the first reptiles appear, so it's very significant. As to the rise of the dinosaurs later, as well as the mammal-like reptiles during the Permian. And this is the age of insects and arthropods. So the oxygen levels in the Carboniferous were massive. They were, I think, 20, 30 more percent than oxygen levels on Earth now, and that allowed the insects to grow massive proportions, and also allowed forest fires to start way more. So this was basically a burning pit of insects, and it was hell. But the tiny reptiles, they were pretty small lizards, didn't manage to survive, and as the oxygen levels dropped, and they went to the Permian, the reptiles grew a lot bigger. You have the famous Dimetrodon evolving in this era. The sailback reptiles, they were mammal-like reptiles, so they did, although they weren't exhibiting live birth, their skeletal builds were close to mammals, and eventually during the Triassic, this build would fully split off into mammals. And the end of the Permian, and leading into the age of dinosaurs and the Mesozoic, was the largest mass extinction event, wiping out 90% of all life on Earth, and starting life anew, basically. This is also when Pangea first formed during the Permian. It would start its breakup during the Mesozoic era. Now we go to the second case study where we talk about the Cenozoic, and the Cenozoic is just as important as the Paleozoic. So Paleozoic, you see the evolution of the first backbones, plants like land life, jawed fish, insects, amphibians, reptiles, mammals, and the biggest mass extinction event to top it all off. The Cenozoic was just as important. So here at the start, you just have the evolution of the mammals, although actually birds, the descendant of dinosaurs, were the ones that really took over the start of the Cenozoic. The terror birds, as they were called, were closer to raptors, but there weren't really any large mammals to oppose them at this time. But this changed drastically. You started seeing the appearance of rhinos with hooves, which were more related to horses than actual rhinos. You had giant sloths. You had bear dogs, large pigs that ate flesh. There were a lot of different things. And during like the Miocene and Pliocene, Pleistocene, you had the development of more famous mammals such as saber-toothed cats, mammoths and mastodons, and basilosaurs, which was a massive toothed whale. And yeah, and at the end of the Pleistocene, we had the Ice Age, and then we have to modern day. So this, again, going back to previously, whoops, this is divided to all of these. The actual periods are the tertiary and the quaternary, and the tertiary is split up into into sub-periods, and the Paleogene and the Neogene, and then there's that split up into 5 epochs. All right. And we can look at the evolution of humans here too. So see how far we are here. Okay. The evolution of humans here. You can see the apes at the top here, as this is what they were. This is around where they branched off from apes with the start of the chimpanzee. You had the Australopithecus, which was the first primitive humans. They were just apes. They're essentially just apes that could walk upright in terms of capability, but their contributions to human evolution is tremendous. They had larger brain sizes. They had more mobility, flexible thumbs. They had more options as to whether they wanted to live on the ground or in the trees. Most of the time they lived in the trees though, because the ground was a terrifying place for them. But as we slowly start to work our way down the human evolution tree, you can see the Homo habilis. This is where the Homo genus starts to pop up first. Branching off the Australopithecus genus. This is the famous Lucy skeleton. And the Homo genus was the first ones to truly start taking life in strides on the ground. They were the ones to start developing fire, tools in Homo habilis and Homo erectus. They started living in social units, coordinated their hunts, their gathering, and all their effort paid off the last 2 builds here. This one is a sort of a what you call it, transitionary fossil between these two, the primitive humans and the more modern day humans. So the Homo sapiens neanderthalensis, or the Neanderthal, was essentially a superior version of the Homo sapiens or sapiens in the time that they were alive. They were much better suited to the Ice Age climate. They had larger bodies and bigger brains, more flexible bodies where they were much stronger, much faster. But the Homo sapiens weren't useless either. They had much more tighter social units. They would also use tools more effectively. And Homo sapiens managed to survive longer because this larger body, this stronger body, this larger brain that the Homo sapiens neanderthalensis required a lot more nutrients and food and sustainability, and that simply just wasn't available at the end of the Ice Age with another mass extinction. And the Homo sapiens were much better suited with their smaller bodies and smaller brains. And although intermarriage and interspecies hybrid did happen between these 2 species, the Homo sapiens were the only ones that truly survived the Ice Age extinction, and this is us today. Now we just went through a brief history of paleontology and Earth. We'll also talk about the conditions in the field, and the actual work of uncovering the bones seems like a straight process. As you can see, there was a lot of examples. These are some of the actual specimens they did uncover. The black parts is what they were missing, but these are still extraordinarily complete for fossils. But the actual external factors making the digging and uncovering incredibly challenging. And as someone who has experienced these conditions, to uncover centers of marine life, the heat, dust, and the time of day can all be extremely detrimental to the ability to dig. And the restrictions on digging are actually seasonal based. So you want to dig when there's the least amount of effort required. So this is when there's no snow, when there's no heat waves, there's no rain. So you want to dig towards the late spring and early summer before it gets incredibly hot, incredibly dusty, or a lot of snow, a lot of rain, where you have the least amount of external factors affecting your progress. Um, so it's only shelved to a couple of months per year where you're actually able to do the digging. And this forces the paleontologist to work in extreme heat as well, because early summer is still pretty hot, even not as hot as late summer, but early summer is still pretty hot. And this risks a lot for sunburn and even skin cancer for being in the sun out for so long, because you have to be out there for a long time. You don't want to work when it's dark, and it could be dangerous depending on the environment where you're digging in. And having to work from basically dawn to from sunrise to sunset, digging and uncovering bones with pinpoint precision to not damage any of the bones is extremely tight. It's extremely excruciating, and the time crunch there doesn't really help your case. So the conditions are pretty harsh for paleontologists, but the payoff in learning about evolution and the history of the Earth makes it worth it. So this all goes back to what you can learn about paleontology. So there are several resources available for you to learn more, but the ones I can recommend you are the several amounts of documentaries you can find for free on YouTube, as well as documentaries on the website CuriosityStream. These two are where I really started taking my passion for dinosaurs and turning it into uh, an actual desire to go into a career in paleontology. Can I see pictures of the eras again? Yeah, sure. Go ahead. Right. Okay. So so I learned a lot from these YouTube documentaries and Curiosity Stream documentaries. Um, there's a lot to learn for you guys too. Some documentaries go into the biology and uh, in my opinion, more interesting lifestyles and redepicting the lifestyles. Uh, there's some great documentaries out there, such as trying to think of the, I'm trying to rethink the name. I think it's called Dinosaur Fight Club, where they find bones of dinosaurs so locked in combat, and they repiece the history, and at the end it shows it all playing out, and the depiction of the events that happened. So that's really interesting, and it breaks down how each bone or each tooth mark or each predation mark or each position of the dinosaur, uh, how they all piece together into one big puzzle. And there's also other great documentaries, just full biology ones, such as Walking with Dinosaurs. It's pretty famous. Although it has a lot of inaccuracies since it was published in 1999, it's still a pretty good watch. And its sister documentaries such as Walking with Prehistoric Beasts and Walking with Monsters, I think, which cover both the Paleozoic and the Cenozoic eras respectively, are also pretty good watches. Um, so yeah. You can also find a lot of more educational fiction, such as I believe Prehistoric Park was one I used to love as a kid. Um, and that's just basically it's fantasy, pretty much. It's science fiction basically. Um, where these people go out back into time, and they do have it's live action, so they do have recreations of these dinosaurs. They observe them in their actual habitats, and you can tell that this was based off of actual bones that they found. It wasn't just winged on a whim. This is based on actual behavior recorded through bones and fossil history. And apart from these documentaries and these science fiction series, there are several talks on TED and TED Ed. I'll show you one after this slide that you can look at, as well as guidebooks you can find online in the library that can give you a lot of insight as to what paleontologists are working on right now. So that's one of the less directly educational TED Talks. Uh, And yeah, so that was just basically about the passion behind paleontology, why people become paleontologists, and what fuels them to go through such long, tedious tasks in order to uncover boats that reveal Earth's history. And so yeah, we end there. Thanks, and you can feel free to ask any questions. Okay, if no one has any questions, then um, believe you guys are free to go. Thanks for coming out, and yeah.